Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Mars Special, Beneath Planet's Surface, Ancient Rainfall and CHAMPS Mission. Beneath the surface of Mars. In the ongoing search to uncover the mysteries of Mars, a significant leap forward has come from the Jezero crater, the landing site of NASA's Perseverance rover. A study led by an international team of scientists, including Dr. Michael Tice from Texas A&M University, has illuminated new aspects of the Martian surface. By closely analyzing rock samples from the crater floor, the researchers have begun to piece together the volcanic and geological past of this ancient terrain. The discoveries point to a planet with a complex and active history, one that may have included the conditions necessary to support microbial life. The Jezero crater was chosen for the Mars 2020 mission with purpose. Once home to a river delta, it is one of the most promising locations for finding preserved signs of life. When Perseverance landed on February 18, 2021, it carried with it a suite of scientific instruments capable of conducting geological studies in remarkable detail. Unlike previous rovers, which were limited to visual documentation and basic compositional data, Perseverance operates more like a mobile laboratory. One of its most important tools, the Planetary Instrument for X-ray Lithochemistry, PIXL, is an advanced spectrometer that reveals the chemical makeup of rocks with a level of precision previously unattainable on another planet. With PIXL, the team focused on rocks in the Moss Formation, a key region within the crater. What they found was more than just stones, it was a record of Mars's geological story. Two primary types of volcanic rock emerged from their analysis. The first was a dark rock enriched in iron and magnesium, containing intergrown minerals like pyroxene and feldspar, along with signs of olivine that had undergone alteration. The second type was a lighter, potassium-rich trachyandesite, containing feldspar crystals suspended in a volcanic groundmass. These diverse compositions point to multiple volcanic episodes, with each lava flow cooling under slightly different conditions, leaving distinct chemical fingerprints behind. To understand how these rocks formed, the researchers applied thermodynamic modeling, simulating the cooling and crystallization processes that would have shaped them. Their findings suggest that the rocks underwent a process known as high-degree fractional crystallization, where minerals crystallize out of molten lava at different stages, changing the composition of the remaining liquid. In some instances, the lava also appears to have assimilated iron-rich material from the Martian crust. This interaction between molten rock and crustal materials further complicated the geochemical makeup of the rocks, mirroring processes that occur in Earth's volcanic systems. What makes this significant is not only the insight into Mars's volcanic history, but also what it implies about the planet's capacity to sustain life. On Earth, prolonged volcanic activity is often accompanied by hydrothermal systems, which can create environments rich in chemical energy, environments in which microbial life can thrive. The presence of similar volcanic processes on Mars raises the possibility that early Mars had regions where life could have gained a foothold. It is not just about the rocks themselves, but the stories they tell about ancient heat, chemistry, and water. These findings, however, are just the beginning. Perseverance is collecting core samples of these Martian rocks and storing them in sealed tubes for potential return to Earth through a future mission jointly planned by NASA and the European Space Agency. Once these samples are brought back, scientists will be able to use Earth-based laboratories to probe their structure, chemistry, and potential biosignatures with even greater depth. While the rover provides an extraordinary level of in-situ analysis, it is still just a glimpse of what full laboratory analysis will reveal. Dr. Tice and his colleagues believe the technology aboard Perseverance is revolutionizing planetary science. The ability to examine textures and chemical data at such a microscopic level on another planet is something that was unimaginable only a few decades ago. Each sample, each mineral, each unusual feature brings new data and new questions. Mars is no longer a silent and static world, it is a complex geological landscape, layered with history and shaped by forces not so different from those found on Earth. The discoveries in the Jezero crater serve as a reminder that the universe still holds countless stories waiting to be uncovered. The Martian surface, once thought to be barren and unchanging, reveals itself as a record of ancient processes that could have mirrored the early Earth. As scientists continue to decode these ancient rocks, what we learn about Mars may not only inform us about a neighboring planet, but about the origins of our own. The rover's journey has just begun, and with it, the story of Mars is being written anew, one sample at a time. When Mars had rivers. Mars today, as captured by satellite images, still shows clear signs of an ancient watery past. Near the equator, networks of channels stretch out from the highlands of the planet, branching in a way that resembles tree limbs and terminating in basins that were once lakes or even, possibly, an ocean. NASA's Perseverance rover, which touched down in 2021, is currently investigating Jezero crater, a location that was once the site of an ancient lake. In the distant Martian era known as the Noachian, a powerful river flowed into Jezero, depositing sediment and forming a delta across the crater floor. The sheer size of the boulders deposited there suggests the river once carried water several meters deep. These features sparked the curiosity of scientists like Brian Hynek and Tyler Steckel, who set out to better understand the forces that shaped this terrain. Together, Hynek and Steckel developed a digital reconstruction of a section of Mars. To do this, they relied on a model originally built for studying Earth's geology, created by Gregory Tucker, and adapted it for Martian conditions. Their team also included Matthew Rossi, another researcher at CU Boulder. They used this modeling software to simulate how the Martian landscape might have evolved, especially in regions near the equator. The simulations introduced water into this synthetic terrain in two main ways, either through falling precipitation or via melting polar ice caps, and let the water flow across the landscape over time spans ranging from tens of thousands to hundreds of thousands of years. These simulations revealed two very different versions of the red planet. When ice caps melted in the simulation, the resulting valleys and channels primarily began forming at high elevations, near the edges of the former ice. But when water came from widespread precipitation, the valleys formed across a much broader range of altitudes, from low-lying areas to regions over 11,000 feet above Mars' average surface level. The way these valleys emerged varied significantly depending on the water source. Water from melting ice produced narrow bands of erosion at specific heights, while rainfall allowed channels to form almost anywhere. These simulated landscapes were then compared to real data from Mars collected by NASA's Mars Global Surveyor and Mars Odyssey missions. The comparison showed that the simulations based on precipitation matched much more closely with the actual distribution of Martian valley systems. Although these findings do not definitively solve the mystery of Mars' ancient climate, particularly how the planet was ever warm enough to support rainfall or snowfall, they do suggest that some form of precipitation likely shaped much of the Martian surface. For Hynek, the implications extend beyond Mars itself. He believes that once flowing water ceased carving through the Martian terrain, the planet entered a kind of suspended state, preserving surface features that may reflect what Earth looked like billions of years ago. CHAMPS, delivering small payloads to Mars. NASA's goal of sending humans to Mars by the end of the next decade under its Moon to Mars program has sparked a wide array of technological developments, including a focus on cutting-edge propulsion systems that will reduce the time it takes to get there. The reduced transit time is crucial not only for speeding up missions but also for minimizing astronauts' exposure to hazardous cosmic radiation and the effects of prolonged weightlessness. In addition to propulsion, NASA is exploring ways to improve waste elimination, water recycling, crew safety, and overall mission self-sufficiency, aiming to make deep space travel more sustainable and cost-effective. A crucial part of this effort involves the advancement of sub-kilowatt electric propulsion systems tailored for small spacecraft weighing around 500 kilograms or less. These propulsion systems, particularly the electrostatic Hall effect thrusters that use solar energy to ionize inert gases like xenon, have already demonstrated their potential through previous programs such as the Planetary Science Deep Space Smallsat Studies and Simplex. Drawing from that foundational research, a new concept called CHAMPS, short for Commercial Hall Propulsion for Mars Payload Services, has emerged. Developed by a team of NASA engineers and scientists from centers like the Glenn Research Center and Goddard Space Flight Center, this initiative proposes using compact high-efficiency electric thrusters to send small science payloads to Mars at lower costs and on more flexible schedules than ever before. The central propulsion system proposed for CHAMPS is based on the H-71M thruster, a miniaturized high-performance version of larger solar electric propulsion systems, capable of pushing a nearly 450 kilogram spacecraft while consuming a relatively small amount of propellant. This technology has been adopted and developed commercially through Northrop Grumman's NGHT-1X thruster, which the CHAMPS missions would employ. Instead of relying on rare and expensive launch opportunities where Mars is the primary target, CHAMPS missions would launch as secondary payloads on flights originally intended for the Moon, such as those under the Commercial Lunar Payload Services program. Once launched, the spacecraft would perform a gravity assist maneuver around the Moon and temporarily enter a near-rectilinear halo orbit. This maneuver not only conserves fuel but buys time until a favorable Earth-Mars alignment presents itself, allowing for an efficient trajectory toward the red planet. The mission plan includes a series of low-thrust maneuvers and cruising phases spanning more than a year before the spacecraft reaches Mars. Upon arrival, it will enter a low orbit just 15 kilometers above the surface, enabling complete coverage of the Martian equator every 5 sols. In addition to observing the planet, the spacecraft will study Deimos, one of Mars' 2 moons. After its 2-year primary mission, the craft will shift to a higher orbit, called aerosynchronous, that enables it to maintain continuous atmospheric observation and act as a data relay for other surface missions. The scientific payload for CHAMPS includes instruments modeled after those already used in Martian exploration, such as visible and ultraviolet imagers, thermal infrared radiometers, and near-infrared spectrometers. With this suite, CHAMPS will build detailed profiles of atmospheric pressure, temperature, aerosol content, and chemical composition including water vapor and ozone. It will also track dust storms, cloud patterns, and weather changes across seasons while probing plasma conditions and magnetic fields influenced by solar activity. These observations will help scientists answer unresolved questions about Mars' atmospheric behavior, the transfer of volatile compounds between its surface and skies, and how solar radiation affects its climate on both global and regional scales. The mission aims to reveal the dynamic interactions among atmospheric layers and deepen our understanding of how weather operates on the planet. Importantly, the CHAMPS concept also supports NASA's broader Mars exploration program, which emphasizes frequent, affordable missions to adapt quickly to new discoveries and engage a wider scientific community. This model not only reduces costs and improves mission flexibility but also aligns with the agency's strategy to democratize access to planetary science and ensure that Mars exploration continues with momentum and scientific rigor well into the future.